Hello, reInvent 2019. I'm thrilled to be here today with Catherine Scott from Open Robotics, and we're going to chat about robots, the robot operating system, and open source tools for building robot applications. Kat, tell us a bit about Open Robotics.
Okay. So at Open Robotics, we create open software and hardware platforms for robotics. We use these platforms to solve important problems, and we help others do the same. So I like to think of ROS as basically Linux for robots, right?
Great. So what are the products built at Open Robotics?
So we basically have two large open source projects that we work on. We work on the ROS, which is the robot operating system, which is sort of a robotics application SDK, and we work on Ignition and Gazebo, which are robot simulation platforms.
Great. So today we're going to talk a bit about the development advantage of using ROS for building open source applications. We're going to talk about the simulation, visualization, and validation tools that developers can use for debugging, testing, and building robots. And we're going to talk about the next generation of ROS development going on today, named ROS2, and how it's used in production robot deployments. ROS is the most widely used software framework for robot application prototyping, development, and deployment. Over 800 maintainers actively support ROS core distributions, and over 2,800 contributors have deployed code for binary release packages. There are over 20 million binary Debian downloads every month across a number of versions of ROS. ROS Indigo in 2014 marked the first long-term support version of ROS, which reached nearly 3,000 binary packages deployed against that distribution. Today we have ROS Kinetic and ROS Melodic built and deployed around Ubuntu 16.04 and 18.04. And next year, in May, we'll have ROS Noetic, which would be the last long-term support version of ROS 1. In tandem, there is a development for the next generation of ROS, ROS 2, and 2019 is a hallmark year for ROS 2 because this year we've released the first long-term support of ROS 2 named Dashing, which will be supported through 2021. Also later this year, there will be available the next version, ROS Eloquent. So Kat is going to tell us why using ROS is critical for robot application development today.
So why ROS? I like to say that ROS allows developers to focus on delivering value, not delivering infrastructure. And the analogy I make is that ROS is to robots what Node or Rails might be to web development. Basically, ROS is a set of tried and true robot design patterns and a set of CLI tools for deployment and monitoring and debugging. These allow you to build your robot faster and not worry about basics. ROS also has simulation tools that allow for flexible designs and a library of hardware interfaces and patterns that let you work with the latest and greatest hardware. Finally, and probably most importantly, ROS is a community of experts that are there to help you along the way. ROS is a set of commonly used robot design patterns. At the core of ROS is a well-characterized publication subscription bus for moving messages. ROS 2 is built upon a DDS layer that can handle various QoS aspects of message passing and improves the process substantially. Both ROS 1 and ROS 2's message bus allow you to inspect and modify the messages at any time. ROS also includes a blackboard system for setting parameters of your robot and analyzing its configuration. On top of all this, there's tools for building state machines and data processing, as well as libraries to help define the robot's state and transformation, and tools to start, stop, and pause your robot software whenever you want. Other common patterns you'll find in ROS are tools for logging and playback of data and events, tools to visualize robot data online and offline, a tool chain for installing, building, and running components, a modular package library allowing for loose code coupling and reusability, modular software interfaces allowing you to interleave C++, Python, and other languages, and many, many other user-contributed tools to help you do stuff like build web interfaces to your robot. So how much time does ROS save? You might be asking yourself this. Let's consider the ROS bag features alone. So ROS bag is a custom message serialization and playback library. I've actually seen this in real-world performance testing on autonomous vehicles, and it can store well over 1 gigabyte per minute of data, probably even more. Most of these vehicles have Many cameras at high fidelity running, as well as Velodyne systems capturing a lot of data. This capability to save data, replay it, query data, and build modules and test against that data is extremely powerful. Just this feature alone would probably take a small team years to reinvent. While there are analogs like Protobuf out in the real world, there are none that are really built for robotics applications. Hardware is less hard with ROS. The ROS pub sub bus uses a common messaging format to move data. There are many built-in messages for common sensors and actuators. Some message types that you'll find in ROS that are baked in include camera messages, depth sensors, LiDAR and radar, inertial measurement units, force feedback servos, power systems, and global positioning satellite data. All of these are easily extended if you want to change the format from a base format. Hardware is less hard with ROS. Many hardware types already have driver packages installed. If you have a camera or a common LiDAR system, you could probably install its drivers with a simple command line command. Cameras, for example, use the sensor messages/image format. This base message can be extended to address user requirements like giving you the exposure of the image or perhaps the gain. But the base message format is pretty commonly used, and there's a lot of tools associated with it. These tools allow you to quickly debug your camera systems. So, for instance, all cameras can use the same intrinsic calibration package, all cameras can use the same RViz package for debugging image information, and RQT can be used to open up image windows at any point to see what the robot is seeing. Another example of where ROS is successful is in programming asynchronous behaviors. Generally speaking, programmers find writing asynchronous behaviors to be very difficult. The ROS node interface makes this extremely easy. Basically, a node can subscribe to a message topic and wait until that message appears. When that message appears, it can process the incoming data and try to make a decision on what it wants to do. If there's a behavior that maybe the node wants to trigger, that's fairly simple. It just sends out another messages. Moreover, in ROS 2, nodes are composable, allowing you to build up complex behaviors from simple modules. Furthermore, ROS enables best practices. In any software environment, testing software is crucial to building reliable systems, and the same is true in robotics. Often we hear it from individuals that hardware in the loop is extremely difficult. Well, sometimes you don't actually need the hardware to test your robot. ROS enables developers to create simulated components using Gazebo and Ignition. Moreover, ROS Bag allows you to record and play back real sensor data to make your test even more reliable. Basically, if you can capture a robot doing something you don't like, or as a failure mode, you can take that ROS Bag data, replay it, and build a test against it. These tools allow developers to focus their time on testing their software, not running the robot. ROS packages also allow you to write clean and modular code. Software in ROS is organized into logical packages. A package might contain ROS nodes, ROS independent libraries, datasets, configuration files, or even third-party drivers. The goal of a package is to build a modular and useful set of functionality. These packages range in fidelity from, say, like weekend hacks and proofs of concept to industrial-grade ARM drivers. ROSDEP works just like a package manager on Linux. It allows you to easily install these packages using a command line tool. So probably the most important aspect of ROS is the developer community. And I'm going to talk a little bit about the resources that we provide. Let's start with ROS Wiki. ROS Wiki, which you can find at wiki.ros.org, is generally our intro place for documentation, how-tos, and tutorials. The wiki generally has about 75,000 daily page views and 100,000 wiki pages with probably on the order of 25 daily edits or more. This is the place you want to go if you want to get started with ROS and understand a ROS package. ROS Discourse is our new community discussion forum. It sort of comes on the heels of a long history of using email listservs to discuss what's happening in ROS. It's the place to go if you want to understand the community, collaborate, make announcements, and share news. Currently, we have over 4,500 users on Discourse with nearly 30,000 posts across 3,000 topics. ROS Answers is the ROS question and answer forum. It's kind of like Stack Overflow, and it actually was built about the same time. ROS Answers allows individuals to ask questions and other individuals to answer them. All of these questions and answers can be filtered by ROS version and different tags to make sure the right community is looking for questions and answering questions. As it stands, it has over 34,000 users with well over 32,000 questions answered about ROS. If you end up having a problem with building your robot, most likely somebody on ROS Answers can help you. Open Robotics also sponsors ROSCon. ROSCon is our annual developers conference. This year it was in Macau, China, and we had close to 600 developers in attendance. These developers came from over 40 countries, with 80% of them coming from enterprises and startups. We also help to enable regional groups to have their own regional conferences in their native languages. This year we had 2 of these conferences, one in France and one in Japan, each with well over 200 attendees. ROS is a federated community. Index.ros.org is the canonical list of packages and repositories that you can use with your ROS robot. This federated model allows you to host your own code or use any of the free services out there like GitHub or GitLab. If you list a package in index.ros.org, it can be indexed, tracked, and searched by the rest of the ROS community. You can also sort your ROS packages by the ROS release and other keywords. ROS represents development tools for today's distributed team. ROS's modular codebase, strong logging tools, and simulation tools empower modern distributed teams. In the past, you needed a robotics lab and a bunch of local developers to work on a robot, and they probably had to share time on that robot. These new software features that I'm going to talk about, as well as the ones I've talked about previously, allow you to work faster and work in a more distributed manner. They also allow you to work with other teams, perhaps academic or developers across the globe. So why don't we talk about some of the simulation, visualization, and validation tools available in ROS. ROS has 3 major tools that you should know about for your development. There's Gazebo Ignition, which is ROS's simulation tool, RViz, which is ROS's online visualization tool, and RQT Suite, which is our online analysis tool. Ignition Blueprint is the latest version in a long line of Gazebo tools, and it's built to work with ROS 2 from the ground up. Ignition Blueprint provides physically based rendering of materials, a GUI for model replacement, payload-dependent battery models, new command line tools, incremental level loading, and distributed simulation capabilities. We're still working on this a little bit. Let's take a look at what it looks like. So you see in the video, here's a little tiny robot in a playground. This is what it's for. It's a playground for robots. On the left, you'll see a depth sensor image, and on the right, you can actually see the robot's camera view. We can also move the robot around and change the view of the world. Ignition supports physically based rendering. Physically based rendering improves the fidelity of the simulation, which can help if you're trying to build simulated computer vision applications across your simulation. It also just makes it seem more realistic. Ignition Gazebo is also more modular than previous versions of Gazebo. Basically what we did is we took the monolithic Gazebo library and decomposed it into Ignition libraries. These libraries can be reused in other applications. Ignition Gazebo is just one particular composition. Let's talk about physics in Ignition and Gazebo. What we found is that no single physics engine is best for all situations. So what we've done is created a common ATI atop all physics engines. This allows you to pick which one is going to be best for your application. And you can choose this physics engine at runtime. To simulate sensors in Ignition or Gazebo, we allow you to build parameterizable models of common sensor types, and we also allow you to build parameterizable models of common noise types for those sensors. And on top of that, there's a common API upon multiple rendering engines. You can also export this sensor data via middleware. All of this means that you can take your ROS simulation and build realistic simulated sensors. Gazebo Ignition Extension. We have C++ plugins that allow you to extend any part of Ignition Gazebo. You can get or set any part of the world between physics steps and extend or add sensors as you need. And you can interface with hardware input devices. You can make fake interactions that are impractical to simulate and delegate interactions to other systems. High fidelity testing, the new approach to robotics R&D. Simulation is quickly becoming the de facto standard for robotics research and development. DARPA has used ROS's simulation capabilities in both the Subterranean Challenge and the Robotics Grand Challenge. What's cool about simulation is that it allows software developers to test and validate robotics concepts at a high level of fidelity without ever having to touch or buy hardware themselves. This allows smaller competitors and smaller teams to validate their concepts in competition. We've also shown that these sorts of competitions work in all sorts of environments. Virtual Robot X showed that this capability works in maritime environments, while the National Institutes of Science and Technology continue to use our simulation approach to validate industrial applications. High fidelity testing with Ignition Gazebo. Ignition Gazebo can be used for unit and integration tests decoupled from hardware. It allows users to create continuous integration and continuous deployment pipelines just like normal software development. This is something that's fairly new to robotics. Users can simulate with physics or other phenomena like power consumption. This capability also allows developers to rapidly test hardware hypotheses without ever touching a robot. This is, say, you can basically try like 5 different kinds of cameras or 5 different kinds of LiDAR before you ever buy one for your robot. Simulation, the power of cloud parallelization. Not only does a simulation allow us to test our robot on our own machine, we can actually put our simulations into the cloud and test lots of different robot configurations in parallel. This means you can not only test 100 versions of a robot or 100 different situations with your robot, you can test thousands of them and do it all at the same time. This allows developers to concentrate on fixing failure modes of their robot, not revalidating the results over and over again. Cloud parallelization approach also allows developers to quickly tune parameters, trying all the different possible values in parallel. Now that I've told you a little bit about ROS and Ignition Gazebo, I'm going to bring in Cam to talk about ROS2 and production robot deployments.
ROS1 was developed with research and development in mind and use cases based around academic development. This yielded a robust and reliable platform which has been used in commercial and industrial settings as well. However, because ROS was built for research and development, it lacks certain basic features like security, reliability, and being able to be certified. So with this in mind, there's a development of the next generation of ROS called ROS2, which improved the quality of design and implementation of ROS1. It adds systems reliability for the distributed networks. It adds native support for real-time control and deterministic execution, which was a key feature missing in ROS1. And it also opens the door for being able to validate, verify, and certificate ROS applications. It adds flexibility in communication by adding quality of service reliability parameters to message communication, and adds support for small embedded devices, which traditionally in ROS1, if you wanted a microcontroller system to publish into the ROS network, you would have to write a ROS driver to support that. In ROS2, there's native support for small microcontroller devices. The core architectural changes between ROS1 and ROS2 is the addition of a ROS middleware interface layer and the data distribution service, or DDS, as the middleware layer, which supports security, reliability, and determinism. Traditionally, ROS1 middleware was based on a custom TCP and UDP layer, which upon the client libraries were implemented above. In ROS2, different vendors can provide different DDS implementations, which customers can leverage and benchmark and decide which one is the more applicable to the problem at hand. DDS is a protocol specification designed by a standards body, much like the post office, where the post office sets the standard format for addresses, zip codes, and letter sizes. Each ROS middleware interface, or RMW, is like the letter carrier such as FedEx, UPS, or the post office, and they use the DDS standard to move letters, in this case, the data. If you need guaranteed next day delivery, someone can provide it. This makes ROS on embedded microcontrollers now possible. The decoupling of ROS messages from their underlying delivery system has greatly improved ROS performance. Each RMW implementation layer can now be validated and verified to confirm its security, reliability, and determinism. The addition of the DDS layer also makes it possible to use ROS in resource-constrained environments like microcontroller or high-volume production robots. Other improvements in ROS include the ROS node lifecycle management, which allows for nodes to have well-defined behavior at every stage of execution. ROS2 also has a new build system, Admin and Colcon, which improve package management and greatly speed up the build times. Admin also creates a development workspace, allowing on-the-fly editing of Python modules and greatly improving the developer productivity. The ROS Client Library, or RCL, unifies the ROS, C++, and Python interfaces, creating a smaller code base that is easier for review and improvements. New ROS2 features are being added with every release, such as the recently contributed zero-copy message passing for large binary messages by Bosch. DDS also provides a security specification, adding security enhancement by defining a service plugin interface, which is natively implemented by every DDS vendor. This allows for authentication, access control, and cryptography, where using a public key infrastructure, messages can be encrypted end-to-end between nodes. ROS development today is managed by a technical steering committee composed of over a dozen companies. AWS Robotics is thrilled to be contributing on behalf of AWS customers to ROS2 development. The technical steering committee not only manages the roadmap, but also sets developer policies, establishes working groups like the tooling working group. Is ROS2 ready? Well, 2019 marked a special year for ROS2 development, on which the first long-term support version, ROS Dashing, was released. ROS2 is designed for production-grade applications, supports multi-platform development, there's no vendor lock-in, and is built on top of open source standards. The permissive open source licenses allow for commercial development and commercial products, and there's a thriving global community of developers and maintainers building on top of it. On behalf of AWS Robotics and open source, Kat and I thank you for joining us today.
Thanks, guys.